Hi class, this last part of Chapter 4 talks about some of the connections between solar activity and the space around the Sun as well as the Earth. And we'll start off looking at the surface of the Sun, talk about those sunspots again that we had mentioned previously, and some of the other things that come along with the sunspots. Talk about magnetic fields that are part of the Sun, very much part of the Sun, and contribute to a lot of the activity. And we'll talk about how we know these things, how can we measure these things. And then finally, we'll talk about how does this activity change over time, and what kind of measurements have we made in the past to see that these changes have occurred in the past. So, what causes solar activity? This is a picture of what's called a solar flare. That's a bunch of material that's about to leave the surface of the sun. It gets ejected so fast that it's leaving at a higher speed than the escape velocity of the sun. So a bunch of material can be sort of shot out into space. So we'll talk about where these come from. So some of the big things that you want to think about when you think about the sun are sunspots, we've mentioned before, solar flares, which I had just pointed out in that picture, solar prominences, and then also the solar wind and the magnetic field. And they're all kind of connected. So sunspots, going back to sunspots, if you look at a sunspot really carefully, you see it consists of a couple parts. There's a really dark part in the center, a very dark part, and it looks almost black. It looks like there's no light being given off there at all. And then there's a slightly less dark part around the edges here. In fact, this very dark part is still very hot. And if you were to just take this dark part out of the sun somehow and put it up into the sky at night, it would glow with the light of almost a full moon. So it is a pretty bright object on its own. But in contrast to all the material around it, it's fairly dim. So the temperature in the kind of the average surface temperature on the sun is about 5,800 Kelvin. The surface temperature in these sunspots is closer to 4,000 Kelvin. So somehow they're cool spots. Somehow the hot gases are not coming up from underneath into these spots. These spots are remaining cool. Remember that normally when you look at these features on the sun, you have these dark areas which are cooler and the lighter areas, the brighter areas which are hotter. Hot gas is coming up in these brighter areas. It's going down in the cooler areas. So somehow we've got this big region of the sun where no hot gas is flowing upward into it. Just cool gas is going down into it. So what's going on? Why is that happening? We believe it's all connected to magnetic fields. So how we know this is when we look at a star. We talked about stars before. We talked about light sources in general, and we talked about different spectra that they have. And the sun, the spectrum that the sun has is an absorption spectrum. The sort of the interior of the sun gives off a continuous spectrum, but a lot of that light then travels through the atmosphere, through the photosphere and the atmosphere of the sun. And so some colors that you see get absorbed. So what this is showing you, this figure shows you that there's a particular color here. Going left to right in this diagram is different colors, and it's all painted green, so it's not obvious. But there's different colors here that would span a certain range of wavelengths. And so looking at in this region, this represents a particular wavelength of light. This would represent a particular wavelength of light as well. And when you get close to a sunspot, what you notice is that this particular absorption color, this particular wavelength that's being absorbed, actually splits into 3 different wavelengths. And that's something we know happens when we put atoms in a magnetic field. So when you put an atom in a magnetic field, without the magnetic field, normally you might see one color that it emits. And remember, atoms can absorb the same colors that they emit. So when you put an atom, say hydrogen or helium, into just all by itself, it'll absorb or emit certain specific colors. If you put it in a magnetic field, those absorptions and those emissions are different. They're slightly different. Some of the colors can actually turn into 2 closely spaced colors rather than just one. And that's what we see happening when we look at the light coming out of a sunspot. We see that there are these colors that have been split away from what was normally absorbed or emitted by the atoms in the gas. So that's a strong indication that there's a magnetic field involved. This is something called the Zeeman effect, the splitting of spectral lines in a magnetic field. It's a very well-known phenomenon in the laboratory when you put gases in a magnetic field. It's very easy to see, it's fairly easy to measure, and it's fairly easy to understand why this is happening. And so because we see it happening on the sun, it's a very strong indication that there are very strong magnetic fields in sunspots, because we see this strong splitting in the sunspots themselves. And the amount of splitting of the spectral line, sort of the distance these different colors are that are being absorbed, indicates the strength of the magnetic field. So it's a pretty strong magnetic field in these sunspots. So if we think about what magnetic field is, we can talk about things called magnetic field lines. And what a magnetic field line is if you think about a little compass that you might hold to find the north. If you ever go camping or you go hiking, you might carry a magnetic compass with you, and one end of it always points north. Well, the way we define a magnetic field line is if you took a little magnetic compass, it would always point parallel to that magnetic field line. So everywhere along this line, the compasses that I might put here would all point upward. On these curved lines, the compass needles that I would put would always point, well, here this one points upward. Over here, though, there would be a line kind of pointing up and to the right. In other words, they always point parallel to the magnetic field line, but the magnetic field lines are curving. Here, this compass points a little bit up and to the right as well. And we'll look at another little animation of this in a minute, but what happens with charged particles, the sun, remember, is very hot, and so there's a lot of free charges flying around, electrons and protons, and these charged particles don't tend to move very easily across magnetic field lines. They tend to move along the magnetic field lines. So what we think is going on inside of a sunspot is that you've got these strong magnetic fields kind of coming out of the sunspot, and the gases from below, you've got these strong magnetic field lines coming out of a sunspot. The gases below have a hard time going into this region, where just below the sunspot. Anything already in this region might flow up or down into or from the sunspot, but it's hard to get gases to flow sort of sideways into this area, so then to flow up into the sunspot. In other words, the hot gases have a hard time. Like here in this part of the figure, these would be the hot gases rising up. They would tend to have a hard time going further over into this region, but right below the sunspot, and then flowing up into the sunspot. They would have a hard time because of this strong magnetic field. What really flows into the sunspot is the stuff that's kind of already there. So it might be coming down from the sunspot, or maybe there's some gas flowing up, but the hotter gases off to the side here wouldn't be able to go into that area. The magnetic field line is almost as if it's preventing gases from flowing sort of sideways inside the convection zone, just below the photosphere. So that's what we believe is going on with these sunspots, is that there's just it's a region of very strong magnetic field that prevents hot gases from flowing upward. There are gases that can flow along these lines, but it's mainly the gases that are kind of already there. It's hard to get stuff to move into that region. And when you look, another piece of evidence is when you look above the sunspots, often they come in pairs, for one thing. So it's like there's this big loop of magnetic field that kind of comes out of the surface of the sun and comes back down again. And one thing you can see is when you compare the spectra of the two different sunspots, you can actually see that the magnetic field is kind of pointing in one direction, perhaps upward, and in one sunspot, and kind of downward in the other sunspot. The sunspots, the pairs of sunspots, have what we may call opposite polarity of the magnetic field. That's one thing you notice. And then gases that do come out, that do escape from nearby the sunspot, and end up kind of traveling along these magnetic field lines. And you get these beautiful arcs of gas that flow up and out, up and over. These are called solar prominences, big chunks of gas or streams of gas that follow these magnetic field lines. They look like big loops of gas. If we go back to, I think I've shown this site before. This is called the PHET, Interactive Simulations, University of Colorado. There's a couple in here on magnetic fields that are fun to play with. And this one in particular is a Java applet. So what it shows here is a magnet. It has a north and a south pole. So magnets have north and south poles. And all these little things here are compass needles. And the white needle is the one that's going to point toward the North Pole. And you can see if I move this compass around, the little white needle is going to point toward the North Pole, like that. And it's always pointing, wherever I put it, I could imagine that the magnetic field line is kind of parallel to it. So, really magnetic field lines are just kind of a way to sort of imagine the magnetic field created by whatever it is that's creating it, a bar magnet in this case. In reality, magnetic field is just everywhere. There's a value for it everywhere. But you can kind of get a sense of what direction it's pointing by putting a compass needle in space and seeing which way the sort of the white end points. This would be the direction that the magnetic field is pointing at this point here. If I move this compass over here, let's say, magnetic field is kind of pointing more downward over here. And then you look at the whole array of little magnetic compasses that we have here, you can kind of see these lines, these patterns that seem to kind of go from one pole to the next, from one pole to the other over here. And so that's what we refer to as magnetic field lines. There really aren't lines. These aren't actual real things. These are just ways of kind of depicting what's going on. Right? So magnetic field is everywhere, even in these locations where I don't have a little compass, there's magnetic field. And one thing to notice is that, or one thing about these sort of pictures, is that the more, and this doesn't show it that well, but the more dense the magnetic field lines are, that's just an indication or a way to represent how strong the magnetic field is. Right? So going back to that last slide, the magnetic field is really strong in these sunspots. We draw these magnetic field lines as being really close together. Going back to the previous picture, magnetic field is very strong in this region where the lines are closer together. Up in this region, the lines are further apart. The magnetic field is a little bit weaker. So that's just one way of depicting what's going on with the magnetic field, like what direction it's pointing and how strong it is by drawing these magnetic field lines. So that's basically sunspots. And so sunspots are caused by magnetic fields preventing hot gases from flowing upward. And these magnetic fields are very strong. But we find there's also a lot of activity around these sunspots. Because of those strong magnetic fields, hot gases from the surface of the sun can be lifted up and ejected out into space. So that's what a solar flare is. This is a picture of this is an X-ray photograph taken in just X-rays, looking at X-ray light given off by the sun. So the photosphere itself gives off mainly visible and a lot of infrared and some ultraviolet, not a lot of X-rays. But where it's really, really hot in the corona of the sun, and we talked about the outer layer of the sun's atmosphere, the corona. In this outer layer of the sun's atmosphere, it's very, very hot. The gases are giving off X-rays, very high energy light. So, and you can see the red here indicates a lot of X-rays. And this is a region on the sun where there are some sunspots. And so this very intense emission of X-rays would be accompanied by like a burst of gases coming out of the sun, a big storm that's almost like erupting off the surface of the sun, ejecting material out into space, ejecting a lot of X-rays out into space. That's called a solar flare. Solar flares send these bursts of X-rays and charged particles out into space. And these are associated again with sunspots because they're associated with very strong magnetic fields. Here's a picture of a solar prominence that we had mentioned earlier. Again, it kind of shows the magnetic field lines as they arc above the surface of the sun. The gases get sort of ejected, but if they're not traveling so fast, they might just kind of travel up along the magnetic field and not necessarily escape into space. And then they might just fall back down again. So they form these nice, beautiful arcs of gas above the surface of the sun. And here's the picture again, the corona, the same picture. The corona appears very bright in the X-rays where the strong magnetic fields are. So there's a lot of X-rays being emitted in this region where their magnetic field is very strong. So somehow the magnetic field is also associated with the temperature of the corona, making it very, very hot. And both the chromosphere and the corona are much hotter than the photosphere itself, which is a little bit odd. You would think that as you move further away from the core of the sun, that the temperatures would continue to cool off. They do cool off until you get to the photosphere, and then above the photosphere, the chromosphere and the corona, they actually get much hotter. And so in the chromosphere, there's mainly a lot of ultraviolet. The temperatures are maybe 10,000 Kelvin or so, and there's a lot of ultraviolet light being given off. In the corona, though, the temperature can get up to about 1,000,000 Kelvin, and so there's a lot of X-ray light given off. And then when the energy gets so high that a lot of material just gets erupted from the surface of the sun, it's like an extreme solar flare. It's called a coronal mass ejection, when just a lot of material, big, huge bursts of energetic particles, as well as X-rays and such, just travel away from the sun so fast that they just completely escape the sun and they travel out towards space. If one of these things headed toward the Earth, it could quite possibly do a lot of damage to satellites orbiting the planet, blacken out radio communications, possibly disrupt electrical power grids, and so on. So luckily we have our own magnetic field that does help us, kind of protects us a little bit from some of these things. So I'm going to go back to another website before we move on to this part about the Earth interacting with the sun. I think I pointed this out in one of my last videos, but there's this SOHO satellite, the Solar and Heliospheric Observatory. And on its website, there are these movies that show the sun doing different things. And what we'll be looking at here is a movie of the sun being blocked by basically a disk so that the telescope, the satellite, can actually observe the corona. And so you can see these bright bands coming out. That's the corona. And we'll see this in a couple different ways. And we'll also look at an image of the sun, the actual, kind of like an X-ray image or an ultraviolet image of the sun, without blocking the sun out at all, but just looking at the sun itself, not in terms of the visible light it gives off, but in terms of like the X-rays and ultraviolet light it gives off. So this picture here, it shows the sun. Watch, there's some things floating around over here. Could be some satellites. Look at this material streaming off the sun. The sun's in here behind this black disk. The sun is represented by this little circle right there. That's how big the sun is. Look at that material coming off. So you can see stuff streaming off the sun. This is the corona. These streams of light coming off the sun. Look at that material flying off there. So there's material just spewing out of the sun all the time. Constantly, the sun is constantly losing material. You can see this is March 5th of 2017, and you can see the time going by at the bottom here. Here comes that amount of stuff, that big amount of stuff coming off over here. There goes that out there, and there's some more stuff that gets ejected over here. You'll see that just in a second here. Here it comes, there it comes, a big burst of material, and then it rewinds. It goes back to the beginning. Here's a similar. Oh, that's the rotating one. Let's go back to this one first. Here's a similar one, looking a little bit closer in a different color, and you can see all that material coming off over here. And you might see a burst of material coming off over here. Here it comes, a big burst of material coming off over here. So again, this is over the course of just several hours. So it looks like things are happening very rapidly on here, but really this is happening over several hours. But also this is the sun right here. So this is a lot of space we're looking at. This is the sun, and so this is twice the sun's diameter out here. And so the atmosphere of the sun really extends very far out. This other picture shows the sun rotating much faster than it really rotates. But this is an X-ray image of the sun. And you can see these really bright spots in X-rays. And these are where the sunspots are. These are where the really strong magnetic fields are. And the sun the corona is getting really, really hot above these regions, above these sunspots. So even though the sunspots are cool, they're associated with really strong magnetic fields that actually heat up the corona and the chromosphere above the sunspots. And you can look at the website again. There's all kinds of other little videos that are kind of fun to look at. And there's some pages in here about some publications and newsrooms and stuff, classroom stuff. So there's things in here that allow you to understand some stuff about the sun. There's a lot of good educational material in here too. So when the solar wind flows out away from the sun, these are a bunch of charged, very high, fast-moving charged particles. If they just slammed into the earth and hit us, that would be good. That would not be good. That would probably do damage to us physically. But luckily our earth has a magnetic field, and that helps take these particles and kind of makes them deflect around the earth. And many of them go past the earth and just kind of go on their way through the solar system. But some of them come down and go in near the poles. They kind of concentrate near the poles, the south as well as the north pole. And when that happens, they interact with the atmosphere, and they produce these beautiful northern lights. And so you can see these, whenever you're near the poles, northern or southern poles, you can see these almost every night. Sometimes the amount of material coming from the sun is so strong that these storms, these solar storms, can be seen even in northern United States, even in southern United States at times. It has happened. So the solar wind can do nice things. It can do beautiful things. It can show you these beautiful pictures in the sky, in a sense, paintings in the sky. But that same energy could disrupt power grids. It could damage communication satellites. So it can do some damage. There have been recordings of power grids going out because of very energetic solar storms. So if you think about what the sun is doing, are there any patterns to what it's doing? Does it just kind of do this stuff randomly? Well, if we look at the sunspots and we look through the past and we look at people that have recorded sunspots and try to take pictures of the sun, we see that there is a pattern. There is about an 11-year pattern of sunspots. We call it the sunspot cycle or the solar cycle. And so every 11 years, the sun seems to get more spots, and then 11 years later, the cycle kind of repeats itself. So there's a lot of spots. For example, in the late 50s, there were a lot of sunspots, and by the mid-60s, there were very few sunspots. And then it increased again around 1970. There were a lot of sunspots. And then it decreased in the late 70s and increased again in the early 80s, and so on. So there's this nice pattern, this very regular pattern of increases and decreases in the number of sunspots that we see. So something's going on here that makes it very kind of regular as far as how the sunspots are created. And if we look at also the sunspots and kind of where they're created on the sun, we find that this is kind of an interesting plot about along the bottom here. If we look at the maximum around 1970, when there was a lot of sunspots, kind of follow that down here. Early on, in around when the sunspot cycle is starting to begin around 1966 or so, there aren't a lot of sunspots near the equator. So this axis is the equator of the Earth, and this is the North Pole, or not the Earth, the Sun, North Pole and the South Pole. So early on, there aren't a lot of sunspots near the equator, but there are maybe some sunspots up near the poles, like in around 30-degree north latitude, 40-degree north latitude, and south as well. As time goes on, we end up getting more and more sunspots near the equator of the sun, fewer than ultimately near the higher latitudes. And so that's another pattern we see. In a cycle, the sunspots start to first appear in the northern and southern latitudes of the sun, and over time, as the maximum approaches, the sunspots appear more and more near the equator of the sun. So it's almost like they kind of travel, in a sense, from the northern latitudes to the equator over time. So it's another interesting pattern, and to try to understand that, we have to think back again to the magnetic field. What's going on with the magnetic field? We'll get to that in just a second. It's hard to go back too far, but we can go back sometime by looking at other records to see what kind of sunspot activity there was. And it turns out that in the 1600s, between roughly 1650 to 1700 in that region, in that amount of time, there were very few sunspots in this time here. Very few sunspots. And so they call that the Mater minimum, because it was discovered by a person named Mater. And it was like instead of every 11 years having very few sunspots, it was a sunspot, sort of a minimum that occurred for like 50 years. It seemed cooler then. They also call it the Little Ice Age. So there's some evidence that these sunspot cycles can affect our climate to some degree. There seems to definitely be some connection there. How strong it is exactly is hard to say, but there does seem to be a definite connection. So what about the magnetic field and how it might create these sunspots? Well, if you think about the fact that the sun is a ball of gas and it's rotating, and it's actually rotating faster at the equator and slower at the poles. It's called differential rotation. So think about a ball of gas that has a magnetic field associated with it. And we can kind of imagine these magnetic field lines that are kind of passing through the ball of gas. Right? So in other words, magnetic field ultimately really comes from moving charges. And the star, the sun, is just a big ball of moving charges. It's a very hot thing, hot gas, that has a bunch of electrons and protons moving around. And so they create magnetic field. And so the magnetic field, if you kind of think about a simple magnetic field of the sun, might look like this. But over time, because the equator moves faster than the poles, the magnetic field lines that are kind of passing through the equator tend to get pushed ahead of the magnetic field that's near the poles. Right? The magnetic field lines seem to get bent. And over more and more time, the magnetic field gets more and more bent. And because of that, the magnetic field starts to kind of get twisted up. And they think that if it gets twisted up enough, it almost kind of forms these knots. And little knots then form, they're little like bulges in the magnetic field that come out of the surface and go back into the surface. And that's where our sunspots appear. So we think that the sunspots appear because of this sort of knotting, this twisting of the magnetic field over time. And what's really interesting about this is that if you kind of look at the magnetic field of these sunspots, you see that you can measure the direction. We've talked about their polarity. You can measure kind of the direction of the magnetic field. And in the next, if you measure the sunspot polarity in the northern hemisphere during a particular sunspot cycle, what you find is that during the next sunspot cycle, when you look at these sunspots, different sunspots in the northern hemisphere, their magnetic polarity has been switched. So the sun's magnetic field actually reverses itself during these cycles every 11 years. The magnetic field gets so twisted up it almost like breaks in a sense, switches itself around, reverses itself, and then starts over again. So that we're pretty sure that's what's going on. And there actually is evidence that that has happened on the Earth as well, that the Earth's magnetic field has actually reversed as well. You know, if we think about the north as being one of the magnetic poles, a compass points north. Technically, the north geographic pole of the Earth is a south magnetic pole. There is evidence from in the past, a long time ago, that the north was actually a north magnetic pole, and it has reversed in the past. So it's an interesting phenomenon, but it definitely seems to be happening on the sun, and it would happen much easier on the sun because the sun isn't a solid object like the Earth is. If you can have hot gases moving very freely, that magnetic field can get twisted up and mangled and twist and reverse fairly easily. But if it's a solid object, it's very hard to kind of move things around to twist up the magnetic field. So ultimately, we've learned what causes solar activity. It's basically the twisting and stretching of magnetic field lines causes these sunspots. And the sunspots are cool, but above them, it seems that the magnetic field is really heating up the gases above them in the chromosphere and the corona, causing all kinds of problems in a sense, sort of. Solar flares, solar prominences, coronal mass ejections, and huge streams of X-rays that can come out toward the Earth and do damage to our satellites and stuff. But luckily we have a magnetic field too that can protect us. So that's it for this chapter, actually. In the next chapter, we'll talk more about other stars in general. So we know a little bit about the sun now. We're going to talk a little bit more general about just stars and kind of talk about different sizes, different families of stars, categorize them a little bit. So have a good night.